So, welcome everybody. I'm happy to see a few friends and colleagues in the audience. And today I'm going to present this work about Polaron spectroscopy of a bilayer excitonic insulator. And this was done in collaboration with Atac, Imamoglu, and Eugene Demler at TTH, Neil Drummond at University of Lancaster, and Richard Schmidt that is now in Heidelberg. So please interrupt at any moment with questions, and I'm not sure I will be able to look at the chat. So if you have questions, please unmute and ask questions. So let's get started. Okay, so as outlined, I will first present what is this interlayer excitonic insulator phase, and then to understand Polaron spectra, it is important to understand which are the bound states of the system. So we will move to the few body physics. And then really to build the Polaron spectra, one can use a Chevy-like Ansatz on top of some BCS bath. Okay, after discussing possible ideas for the future, I will also like to tell a couple of words about some spin-off of this work with some application to 3D atomic superfluids. So, ground state interlayer excitonic insulator is something can be explained like using this setup. We consider two layers of material, and let's say upper layer and bottom layer. By the way, you see my mouse. Oh, great. And if the conduction band of the orange layer is close enough to the valence band of the blue layer, interesting things can happen. In particular, close enough means energy difference less than the binding energy of an interlayer exciton. So what happens? So when we approach, make the two bands closer, it will become convenient to reduce Coulomb repulsion by moving an electron for the blue layer to the orange layer, to the orange band, and this can be favorable if the hole is correlated with the electron. So we create correlated particle pairs, and this can lower the energy. So somehow, at least in the BC regime, this phase can be seen as a ground state, a quantum guess of interlayer excitons. So such a phase has been realized by the Cornell group in last year, and using two layers of transition metal dichalcogenides separated by an HBN layer that basically prevents tunneling between the two layers. So they reported some evidence based on electrostatic compressibility measurements, so some capacitance measurements, and this gives some insight about the pairing, because paired charges will screen applied voltages differently than free charges, basically. And also the estimated binding energy of the interlayer exciton in this case is 25 MeV. Okay, so let's come to a more specific model. So we can consider two types of fermions, electrons in the conduction band or electrons in the valence band. And these bands have opposite effective masses. But if we for the valence band, we reason in terms of holes, then we get a symmetry between electron and holes. In this talk, I will always consider the particle hole symmetric case. That means that the electron and the holes have the same chemical potential and the same mass. So now the other ingredient is Coulomb interaction. So we will have an intralayer component that is repulsive, and an interlayer component that for electron and hole will result in an attractive interaction. So when I say Coulomb, by the way, in this case, I mean some screened version of the Coulomb potential that is called the Keldysh potential. And for the interlayer distance, an important ingredient is the interlayer distance between the two layers that will give a factor in momentum space like a to the minus qd, typically, at least for Coulomb. Okay, so now on top of this model, one can do a mean field theory, and based on some BCS-like variational wave function, and the order parameter that emerges, so the symmetry that is broken, is the U1 symmetry associated with the simultaneous conservation of charge in the two layers. So in the original model, the charge is conserved independently in the two layers. In this case, only the total charge is conserved, basically. And the order parameter is a gap function, very similar to the BCS case. In this case, delta would depend on momentum because the interaction is not contact-like, but is Keldysh. So in practice, in an experiment, one will be able to tune two main knobs that are the electron and hole chemical potentials, and also the interlayer distance. This one will need to build probably different samples. So one in the end gets a phase diagram like this as a function of mu and of the interlayer distance. And in mean field theory, one can predict, okay, there will be the white phase in which one has no charges. So this is the neutral semiconductor. Instead, in the one phase, one will create a spin polarized, a spin valley polarized condensates, while in this phase 2, one can have different polarization. So valley polarization is another open issue that with the electrostatic measurements one cannot assess. So also one can look at more refined phase diagrams like given by diffusion Quantum Monte-Carlo, and one will see that there is actually the excitonic, the condensate phase that is not omnipresent at finite. I mean, when you have charges, but you will rather form a plasma phase in which the electron and the holes are not bound to each other, and but still there is some excitonic condensate region, and also possibly some quadriexciton more complex phase. So the other big ingredient or main tool in this talk is Polaron spectroscopy. So in the last year, this has proved as a very useful tool to investigate the many body phases that one can have in into the materials like transition metal dichalcogenides, which have a very strong optical response, and also spin locking, Valley spin locking, that is something that helps for like studying the polarization properties of a given phase. And so, just to mention a few examples by our group, by our experimental colleagues, and one can probe quantum Hall phases and the correlated insulators in some moiré potential and the Wigner crystal. This has been done in the last few years, and other groups have shown other interesting results. So now, in this spirit, we want to apply Polaron spectroscopy to the excitonic insulator. So what we hope to get from such an experiment? Okay, these are theory talk, but I mean, one at a certain moment would like to do this experiment and get some valuable information on, for example, the density of exciton and charges, the size of the pairing gap, and on the polarization of the condensate, if it's Valley polarized or not polarized. And I will not focus much on this polarization issue because it's somehow straightforward, in the sense that as I was mentioning, in TMDs, we have typically spin valley locking. So it means, and on the other end, we have like trion formation, polaron formation, that is spin selective. So if I have a spin up charge in my bath, I need to inject an exciton with a spin down electron in order to bind to the electron in the bath. And only in this case, I will see an attractive polaron, so a bound state if you want. So this tells you if the charges are polarized, have a given value of spin polarization, it is straightforwardly seen in the optical response. So in the rest of the talk, I will not consider spin degrees of freedom for this reason, because it's very straightforward somehow. And then one may hope there are other interesting questions that are way off from a capacitive measurement, probably, or at least a direct signature is out of the realm of a capacitance measurement. And these are the local coherence of the condensate or quasi-condensate, and also the onset of the BKT transition. So these two points will not be addressed in this talk, will require very different techniques. Okay, so far so good. Okay, so let me go on, and let's move to the few body problem. As I was saying, in this Polaron spectroscopy, one main ingredient is this attractive Polaron. This attractive Polaron somehow originates from the presence of some bound state, that in this case is a trion, so an exciton that binds to an electron present in the system. So to understand the position of this peak, for example, it is necessary to understand the binding energy of the trion. So here the point is that in our ground state we do not have electrons, but we have interlayer excitons. So what we want to do is to compute the binding energy of a probe exciton that will be an intralayer exciton, and a ground state exciton, a bath exciton that is an interlayer excitons. So this requires to solve a four-body problem. This can be done using some diffusion Quantum Monte-Carlo and using realistic values that chosen to match the experimental exciton and tryon binding energy, basically. One can compute the binding energy of this biexcitonic object, that is once again the bound state of an intralayer exciton, our probe, with an interlayer exciton, our object in the ground state. Also, one can compare this guy with the energy of the tryon, where we do not have an interlayer exciton, but we just have an exciton, an electron in the bath. And then one sees that the two energies are close, but in principle different. And this difference is something that is typically larger than the line width of good samples. So it can be resolved in experiments. Actually, this difference between the binding energy of a tryon and of this kind of biexciton may actually have already been observed in a kind of different flavor of excitonic insulator. Here, basically, the idea is that we have two layers. In one layer, we have a moiré Mott insulator. And if we apply some bias, you can transfer some charges and keeping the total filling to 1. And if you do a particle transformation, these are kind of excitons. So this is an experiment, once again, by the Cornell group. And looking at the attractive polaron, you see a jump around the value that at which that is nu equal 1, at which you form the interlayer excitonic insulator. So one possible interpretation of this jump is that here you are observing the tryon binding energy, while on the top half you are observing a biexciton binding energy. But this is a kind of a speculation in the sense that it's a bit different, the system, so one should compute a bit things. Okay, now, so this was the few body problem. That is the super important ingredient then to understand Polaron spectra. So now let's come to the Polaron spectra. So first of all, in the few body problem involves a 4-body problem. So since now we want to do a Chevy-like Ansatz approach, we need to simplify a bit our model. Otherwise, we would need to treat a 4-body problem with some exact diagonalization technique that is very difficult on top of a bath. And so we need to the approximation we make is that the intralayer exciton, our probe exciton, will be a point-like impurity with no degrees of freedom, and with no internal degrees of freedom, just with some momentum, some kinetic energy, and the interaction between the exciton and the electron will be modeled in an effective way by some potential that goes like 1 over r to the 4. That is what one would expect for a charge object interacting with a neutral polarizable object, like the exciton. And we fix W0 in order to recover some given binding energy, in this case 20 MeV, that is close to what one observed in experiments. Okay, so this was how now we need to treat the impurity, our optical probe, and now we need to treat the bath. So this is just the electron and the holes in the valence and conduction bands. So for this there is no impurity, and the basic physics is that electrons are attracted to holes and bind to holes and condense, And so this can be captured by a BCS-like state, variational state. So BCS theory here is implemented in this way. And we do a Bogoliubov transformation. So we rotate the original fermionic operator to get some quasi-particle operators alpha and beta. And we say that the ground state is the vacuum of the beta quasi-particles and the field state with alpha quasi-particles. So it is kind of maybe easier to look at this picture. We have a bare valence band, and this is in the BCS regime. We have a bare valence band and a bare conduction bands. These are coupled by Coulomb. We create a gap given by this delta, 2 delta. And then we fill the lower band, basically. So now we want to implement this. This is generalized Chevy Ansatz. What is the idea? Usually it has been proven very useful for the Fermi Polaron problem in particular, to say that an impurity gets dressed by electron excitations. In principle, one could dress the impurity with an infinite number of particle excitations, but it turns out that it works, one can get qualitatively results if one truncate to just one particle pair excitations. So now, in our case, the neutral excitations are alpha to beta excitations, in the sense that we take an alpha and we excite it to a beta quasi-particles. So it is kind of natural to write down this generalized Chevy Ansatz, and we still truncate to one pair excitation. So the optical spectra will be given by the eigenvalues of the Hamiltonian in this subspace, weighted by psi 0 squared. That is the bare exciton. And also notice that we always consider a polaron with total momentum 0, basically because we inject excitons optically with a wavelength that is much larger. So lambda is much larger of any typical excitonic trionic length scale. Okay, and then what we do is to solve the Hamiltonian diagonalize the Hamiltonian in this subspace with the Keldysh potential and the effective potential that I mentioned before. Okay, so the results one can get are something, are spectra like this. These are plotted as a function of the density. Once again, I'm constraining to particle symmetry. This means basically in an experiment, this would correspond to change a top and bottom gate in the same way, so that the hole and the electrons are balanced, but can become more populated, let's say. So, so I can change the density. I can plot for different interlayer distances. For small interlayer distances, my interlayer exciton will be very well bound. And I see very well the characteristic energy of this biexcitonic state. Also, the quasi-particles gap probably prevents the repulsive polaron to blue shift and to gain oscillator strength. It is known that to have the attractive polaron to repulsive polaron, no, vice versa, the repulsive polaron to attractive polaron oscillator strength transfer, it is very important to have a continuum of excitations. Here I'm gapping my quasi-particles, and the repulsive polaron looks quite flat. So when I increase the interlayer distance, my interlayer exciton become less bound. And what I see is that I get closer to the original Fermi Polaron spectra. So imagining that my all layer is very far apart, because usually I put the exciton in the electron layer, let's say. And also there is this interesting thing that a third peak appears. A secondary peak appears in the spectrum. So what's this? So if one looks at the wave function of this secondary peak, one realizes that this has basically correspond to putting a hole in a 2s state. Basically it's like I'm binding my impurity to an interlayer exciton excited in the 2s state. So this means also that this peak occurs for gap energies, for gap values that are comparable with the trion binding energies. So somehow this gives an idea of the size of the gap. And as I increase the interlayer distance, I see that the attractive polaron goes from the binding energy of the interlayer, intralayer biexciton to the binding energy of the simpler trion. Okay, so now one can ask what is the relative importance of these different processes. And so here is what I showed you before, diagonalize the Hamiltonian, the complete Hamiltonian in the Chevy subspace. Here I neglect the terms that are like the impurity that scatters with the hole. And I see that I get not a big difference, and this is usually the same thing that happens with the Fermi polaron. The hole, in particular at low density, has no phase space, so can't really scatter. Is more interesting the third panel. So the third panel is what one obtains if considered non-interacting quasiparticles. So with this, I mean that usually in textbooks, sometimes in textbooks, one sees the BCS Hamiltonian in this way. One takes the full Hamiltonian, does the mean field approximation at the level of the Hamiltonian, gets a quadratic Hamiltonian, diagonalizes it, and finds something that is three quasipart, basically something that is that describes the evolution of three quasiparticles. And this is the BCS Hamiltonian. Well, actually, if one does this approximation in this way at the level of the Hamiltonian, one gets a spectrum that is not physical at all. What one should do is to take the full Hamiltonian and diagonalize it in the variational subspace. The difference is that now the quasiparticles will interact, and somehow the quasiparticles will attract each other and form Cooper pairs. And this is seen even better now. Okay, so let me come to this in 3 seconds. Let's discuss in general the limitation of this approach. So the first obvious limitation is that we are treating an in principle very complex ground state with the mean field, the BCS theory. So in particular, this means that we are putting coherence from the beginning in our model, and we will not be able to ask questions like are the exciton coherent or not coherent. So the other big approximation we have done is that in computing the polaron spectra, we have reduced our 4-body problem to a 3-body polar problem. And this means that in particular, this behavior of the attractive polaron energy is probably not what one would expect in reality. One probably should expect more something like this, not even monotonic, maybe. And this is why at the beginning was so important to compute exactly the 4-body bound states, because we know that at least in the low density regime, these four-body binding energies are the exact binding energies. So this will give the correct binding energies. So one should take this graph and replace this attractive polaron with this four-body binding energy, and one can hope that this is more or less correct. And by the way, this difference that one is actually dealing with a four-body problem is one big difference with the BCS polarons in cold atoms. And the other big difference is that one has contact interactions in that context. Okay, so the other limitation that is I want to spend a few more words on is that we are doing this Chevy ansatz on top of these other approximations, and in particular, this means that we are restricting to the space of just one pair excitation. In principle, what one should do is to consider the impurity to scatter with the neutral excitations of the system. So let's see what are the neutral excitations of the system. So if we do the Chevy subspace, we get the central panel. And already we see that we have a lot of interesting features, because this line here is what one in superconductivity would call the Bardasi-Schrieffer mode. And in the atomic limit, this is like the 2p transition. And this is the 2s transition, or in the condensed matter Gergo is the X mode. So we see that these are kind of not really collective modes, in the sense that we obtain them already at the one pair excitation level. So they are not so collective. Instead, we see that we have this other mode that should be a Ghoston, but is slightly gapped. If one does time-dependent Hartree-Fock theory, that is nothing else but Gaussian fluctuations, if you want, one gets the same result, but from this Ghoston mode. So one question is, we are missing something about the Ghoston mode. Is this so important, so bad? We don't know. One may argue two things. First, that the Ghoston mode is mostly phase-like, so maybe it is, since the interaction with the impurities density-like, this Ghoston mode does not play a huge role, at least in this region. At least that is like less than one over the Ealing length. And also the other argument is that this difference between these two theories is very small at low density. So at least at low density, our results are in this respect exact. Okay, so by the way, also notice this left panel. This is what happens if you consider just the BCS Hamiltonian. So what I was saying here. So you just get basically the two-particle Hall continuum. Okay, so as I was saying, work will be soon done in the directions of modeling in some way this four-body problem, and not just dealing with a three-body problem for the Polaron, let's say. So the Polaron, the Chevy ansatz somehow captures exactly the three-body problem. So also, as I was saying, this problem of the Ghoston, we don't know how much severe it is. One could hope to do a Gaussian state treatment. With this, I mean, one can go in the Lillo-Pines frame, where the impurity acts like an external potential, and one can basically construct a Gaussian ansatz for the fermions. And when one transforms back to the original frame, the exciton will appear in the exponential with these seemingly terrible terms, but at least the ground state of this problem should be possible to solve. The spectrum may be very difficult. And then one other big question is what happens when the condensate is not really a condensate, but this would require completely different techniques. So since I have other 5 minutes, I would quickly mention that this same BCS Polaron formalism can be applied to 3D Fermi superfluids of ultra-cold atoms. So in this case, what one has is one has 2 fermionic species with some contact attraction. And now we consider an impurity that is another atom which can have 2 different internal states, spin up and spin down. Only the spin up state, we assume that it is interacting. So when the impurity is in the down state, it is completely non-interacting. So if one does some kind of 1D so if one does some usual Ramsey Polaron spectroscopy, that in practice could be some radio frequency spectroscopy, one gets spectra that have just 1 frequency, somehow are 1-dimensional spectra in the frequency. And qualitatively, this is not so far from what I showed you before. The plot is very different because it's expressed in terms of the scattering length, but and not of the density, but the physics is very similar. And there was a recent proposal by Wang and others. I forgot to put the reference, but you can find it in my preprint. Basically, they proposed to do 2-dimensional Polaron spectroscopy that in the end will mean to do plots in terms of 2 frequencies. But the idea is that one can do 4 Rabi flips with some 3 and with 3 waiting times somehow. 3 different times between the different pulses, and one can Fourier transform with respect to the coherence time and of the waiting time and of the detection time t, and then one is left with just 1 time that is called waiting time, and let's say we put it to 0 for big T to 0 in the next. But the important thing, I think that the important idea is that usually with 2-dimensional spectroscopy, one can hope to get some extra information about a system. For example, one can distinguish between incoherent energy transfer between 2 states, or whether the 2 states are coherently coupled, in the sense that are the eigenstates of a conservative system. So in this previous proposal paper by Wang and others, they applied this idea to the Fermi Polaron. And basically, if you can write down an analytical formula, some kind of Lehmann decomposition for this spectral function, if you want. And the important thing is that you have some denominators with some omega minus E up, and E up are the eigenenergies of the interacting systems, while then in this other denominator, you see that you have omega minus E up plus E down, and the E down here is an eigenenergy of the non-interacting system. So imagine that this is, so one could naively think that this one could substitute this E down with the gap. And so in the 2D spectra, one could naively think that one can observe the gap in the 2D spectra. while in linear spectroscopy, once again, one would just probe this other exponent. So I tried this out since it seemed promising, but it turns out that indeed this term gives a contribution that has a different pole than this other term, but this pole is always picked at basically around the zero energy. So basically this tells the take-home message of this paper is that one cannot really gain more information using two-dimensional Polaron spectroscopy, like at least one will not able to get the dimension of the gap. And okay, basically this is this digression of this other spin-off paper. But to wrap up the main talk, I would say that this Polaron spectroscopy tool is now aimed to investigate more in details this interlayer excitonic insulator phase. And what we have predicted that we can get is that we can have a direct proof of exciton pairing by measuring the binding energy of this interlayer exciton, intralayer exciton bound state. So this bound state, this binding energy will show basically that you are not binding to an electron, but you are binding to an interlayer exciton. Also, if one can get to a regime where this secondary peak is observed, one will know that the gap is approximately given by this the binding energy of the tryon, so 25 MeV. And once again, Valley polarization would be rather straightforward in this constant. So I would like to thank you all for the attention, and if there are questions, they are very well welcome. Yes, Sarah?
Thank you very much, Ivan, for the talk. First of all, can you hear me?
Yes, thanks.
Okay, thank you very much for the talk. So yes, I have a question actually on the main part of your talk. If you go back to the when you show like the spectra of the polaron, so yeah, that one, perfect. So yeah, like I have a bit of confusion because in the d=1 HPN case, so you are saying that the appearance of the attractive polaron mode is associated is at the energy of the bound state of the biexciton, or your biexciton. But then just after this one, you also, on this picture on the left, you are saying that the secondary peak is also associated to the bounce to this biexciton bound state. So I'm a bit confused how you.
Okay, I see. So basically, the claim is that this peak. So basically, the idea is a bit like this: when I inject my impurity, I can bind to the best state, and this would be this line, or I can bind to an excited state. So if you look at the wave function of this state is one impurity that is bound basically to a 2s interlayer exciton. So and also you see that this state become bright when you cross the exciton energy. So this tells you that to excite to the 2s state, you are paying some binding, some energy, some fraction of the Rydberg energy. And but in this model, this energy would be order of delta.
Okay, so yeah. So this other my second question would be so the gap, so the delta, the estimate of the gap depends on the difference in energy between these two peaks. So from the secondary peak to the previous one, I mean the trion. Okay.
Exactly, but it will be very rough. So let's say. Okay. Probably like you can say that delta is twice ET, something like this.
Yeah, no, it's a very interesting conclusion. Okay, thank you very much.
Thanks for the question. Yes, please, Benjamin.
Hi, can you hear me?
Yes.
Thank you for that talk. So I was running, I'm a bit unfamiliar with Polaron spectroscopy. And so to be sure, the process will be you're injecting, say, optically an intralayer exciton, and here with this spectroscopic measurement, you're measuring the binding energy. Does this necessarily rely on the Brackwin presence of these excitons? A different question is, like, how would I expect these spectroscopic plots to look, right, when you drive into a normal state for those same bilayers?
Yeah, okay, so excellent question. So let's say you have a normal state, so a Fermi C with some electrons, and you do these optics. Qualitatively is not very different from what you see on the left. What you would see, I don't know if I can use a blackboard, no. Okay, but what you would see is that this repulsive polaron will like blue shift in a more evident way. And also this binding energy would not be here, but would be more like here at the energy of the trion.
I see.
So qualitatively, and to answer your first question, how bright are these resonances? So what happens if you change the density of electrons in the bath? So of course, if you have no electrons in the bath, you will see just the bare exciton. So just this line at 0. When you start injecting electrons, this other line that is called attractive polaron will gain oscillator strength. So you see that it becomes brighter. And yes, basically this is.
I see, but I suppose a priori when you see a spectrum, you can't necessarily then assign if it's a trion or a biexciton.
Yeah, it is non-trivial. So also this let's look, for example, at this plot. That this is an experiment. So what you have in an experiment is typically a bit different in the sense that, well, in this case it's not as different, but okay, so this case is a bit difficult because you have the excitonic insulator that forms above nu equal 1. So in this case, you see that there is a jump, and this is something that maybe you could hope to see. Or in another experiment that in one you would use a setup more similar to this. One could really expect something like this. So one sees, yeah. Okay, so this is not. yeah, it is not completely easy to see it in an experiment. So what I would propose to do for an experiment would be something that is not captured by this theory, but it is, okay, let's dope one layer with a Fermi C, and in this case we will see the trion. Then let's take the whole layer and let's start to dope the whole layer until we reach a balanced a particle symmetric scenario in which we have the same number of electrons and those. And in this case, one should see these more complex binding energies. What one sees in between is not completely obvious.
I see.
But
yeah. I sort of think that naturally, right, if you drive the density here of the electrons and holes too large, right, they usually melt away excitonic order, right? So
yeah, exactly.
I would expect to see some. Yeah. And I guess a follow-up question is if from I could glean you sort of modeled, or your mean field solution kind of produces an excitonic insulator that is very much in the BCS kind of side of the BCS-BC kind of crossover. I suppose that makes for an interesting biexciton because the one you pump optically, the intralayer one, is very localized, and you have this BCS sort of soup of electron and hole that is very delocalized. These results kind of change if you have an excitonic insulator that's on the BC side of the crossover, or is there any reason to think that just the materials realize a BCS regime?
Yeah, this is a very good question. I think at least the experimental claim in this paper is that you can tune from the BC to the BCS crossover. So they show some thermodynamics that is not very, I would not say that is direct evidence, but maybe one can tune from the BC to the BCS crossover. And what would happen is exactly what you say. In the BC regime, in which basically here the BC regime, okay, so more than the BCS regime, the regime in which the Cooper pair size is much larger than the trion is much larger than the trion size. What would happen is that you create basically you effectively break the Cooper pair to create a trion, and then you put back the part of the pair. But basically, in this case, your Cooper pair becomes a trion plus the whole, let's say. And so this is this occurs in this theory at large interlayer densities. And indeed, you see that in this case, the energy of the biexciton matches the energy of the trion. Okay, I didn't say it very clearly, I think, but so basically in the very deep BCS regime, you see the trion binding energy because your Cooper pair is very large. So effectively, it's like you have two very weakly coupled Fermi Cs, and you form the trion in the upper layer, let's say.
Right. Okay, no, thank you.
So somehow it is more interesting the BC regime. Okay, there are other questions? Well, if not, I would thank you all for listening, and I hope to see some of you that I know soon. And thanks again, and see you soon.